So then we can pull back. Let gamma be a p+1 form on U. We calculate, right? We calculate. What can we calculate? Many things. So we can calculate that G composed of J1, let that guy pull back gamma. That's equal to the identity pulling back gamma, right? So by properties of pullback, that says that J1 pullback of the pullback under G of gamma is equal to gamma. The pullback of the composition, the order, it goes the other way around. I don't know if we ever hit on that before, but when you pull back a composite, you end up, it's kind of like inverse. So G composed with J0, pullback gamma is what? It's the constant map, pullback gamma, but that's 0, right? So that implies that the pullback under the J0 map of the pullback of gamma under G is 0. So by K lemma, by the K lemma for omega equal to the pullback under G of the form gamma on the cylinder, what does that give us? Well, that gives us that K of D of G pullback gamma, right, is equal, plus the differential of K acting on the pullback of, the differential of K acting on the pullback of gamma under G, well that's equal to gamma. However, we have proved that pullbacks and exterior derivatives commute. So what else do we know? But you know, the exterior derivative of G pullback gamma is the same as the pullback of D gamma, right? Thus, that gives us the following super awesome formula, namely it's the most bigly formula we've come to today. It's very bigly. Very bigly. K of G pullback D gamma plus the exterior derivative of K G pullback gamma is equal to gamma. So finally, we can come back to the statement of the Poincare lemma, which is that if the set is deformable to a point, then it's closed if and only if it's exact. A form is closed if and only if it's exact. We already know that exact implies closed. So the interesting question is now, okay, so if gamma is closed, then D gamma is equal to 0, right? And if U is deformable to a point, then there exists G such that this happens, right? Hence, gamma is equal to the differential of K G pullback gamma. Because notice that the pullback is linear. So if d gamma is 0, G pullback of 0 is 0, and by the way, K of 0 is also 0. Okay? So the first term goes, and the case is closed, and you're just left with the exterior derivative of a particular function. So not only does the Poincare Lemma proof that I show you here prove the converse in the context of the space being deformable to a point, it tells you how to, it gives you a formula. It straight up gives you a formula to calculate the potential form. This is very cool. This is very, very cool. So what I do in the notes next at this point, and I probably shouldn't go over today because we'll run out of time if I do that. But if you look ahead a bit, oh man, did I not, where'd it gone to? Oh man, did I take that out? Oh.
It's not your...
Maybe that's too, maybe that's, oh, here it is. Duh. It was just here. So like, if you look at page 268 in my notes, my 2015 notes, I think it is, I actually do this in I do it for 3 dimensions. I guess the question is, like, so this is called a deformation retract, if I remember right. This G, okay, so fair enough. Like, to actually put this into practice, you actually have to be able to calculate the G to make it so, right? So on page 268, I basically say, okay, so like for n equals to 3, let me erase this piece here. Maybe I can just sketch, let me just try to sketch the, I won't go through all the calculations, just give you a quick, application to R3. So like, I can look at G of T comma R equal to TR for all, I'll put a vector on it for the sake of clarity, for all R in R3. So that shows you that R3 is deformable to a point, right? So it's smooth, right? And what's G of 1 comma R is R, right? G of 0 comma R is 0, right? So this is the deformation of all of R3 to the origin. We can smoothly contract R3 to the origin. And let's see here. So what I did was looked at, so I'm trying to find out what I'm, so I suppose I've got omega F equal to the usual thing, P dx plus Q dy plus R dz, right? So suppose you have this guy, and so I basically work out on the notes here that the V of XYZ, if you want to calculate the potential it's minus k times the pullback under g of the flux form of the vector field. And if you look at that, what it ends up giving you is straight up the integral of f dot dr over c, where c is a path which goes from, I don't know, I don't say. Oh, it's just along the line with direction x, y, z from the origin. So this is just like origin x, y, z, c, that's c. I don't know if I threw in the minus there for the sake of comporting with like physics, potential energy stuff. It feels a little suspicious. I haven't read my own notes carefully enough to know for sure about that. But then I did the same for like a 2 form. Oh man, I guess I threw that out of the notes. I used to have a calculation. Maybe that's in a future year. Oh well, anyway, that's enough of that. The point is, you could use this to actually like calculate potential forms. And I've tried it out. It's actually, if you fuss with this, so like in the case of a 1 form, it's just going to build you the thing we actually do in Calculus 3, which is for a conservative vector field. The path independence allows you to construct the potential by just picking an origin point and doing the integral of the vector field along the curve. This minus doesn't belong here. It depends on what I mean by V, all right? So here V would be like actually potential energy, which there's a minus that comes from that for physics. But anyway, the interesting thing is if you hit a 2 form and you wanted to calculate the potential for a 2 form whose that was, you know, satisfying the closed condition, you can sort through this stuff and it will actually derive the formulas for like the vector potential. If you've studied physics more, there's a way to write down the magnetic field from well, anyway, I can't say more without getting into a lot of physics here, so let me stop there. Anyway, let's break for like 5 minutes, if you don't mind, and then start again. Is that okay?
Yeah.
Yeah. I'm trying to finish today, so yeah.